Hi everyone, let's talk about first order linear differential equations. Okay, so we're gonna start classifying these pretty specifically. I think this will work a lot better. So this is gonna have a very specific form. It's gonna have some a1, and this can be a function of x. Okay, time times dy dx. So the first order, so it's only gonna have one derivative, right? And it's going to be linear in the dependent variable. Okay, so then I'll have a naught of x, or a0, however you want to say it, times y equals, and then we're going to equal it to g of x. There's a few options here. Okay, so this um, is linear in this dependent variable y. Okay, because it's only y or y prime to the first power, right? So by doing that, then we can work off of this. Now, there's something to be said here. When this thing here, this function g of x is equal to 0, the differential equation is homogeneous. You'll hear some homogeneous or homogeneous. Okay. And if we divide by this term here, then we can get a slightly different thing, right? So we'll divide everything by it. So a1 divided by a1 will just be, 1. This one we can divide, so I'm going to get, oh, I should have copied that. So we're going to divide this, and likewise, we're going to turn this one into a fraction, and we're going to be able to divide by the same thing. Okay, so then we're going to rename this. Okay, this is now going to be y prime plus p of x y equals f of x. Okay, where p of x is these two things divided and f of x is these two things divided. And this thing here is now standard form. Okay, perfect. So now that we have a standard form to talk about, let's put up a few theorems. Let this function and this other function, okay? So you can imagine, because they were made from dividing stuff, so we're worried about a domain issue, right? Like if this is x minus 1, then you don't want x to equal 1, in which case you're going to have a domain issue. So let these two things be continuous on a domain interval I. Okay. Now, it's possible that we could also say continuous and differentiable, and that would really strengthen what we're going to do. But in this case, we can get away with just continuous type functions, and we can dodge that issue. So there's another little key fact, okay? If you have two solutions of a differential equation, you can add those together and make another solution. Okay, and we want something to be both existent, we know a solution exists, as well as unique, we know we have the only answer, and the best answer would be all of the possible answers added together. So we're going to use a solution, okay, let the solution be, and then it's going to be, let's do y of x, and that's going to equal two things: a common solution or complementary solution, or whatever you want to call it. I'm going to call it a common solution in my class, and a general solution. No, a particular solution. And we're going to name this guy general. Okay. Most books, this C is going to be called complementary. I call it a common solution. It comes from a common terms. And then this is a particular solution. And that one's going to be a very specific thing. So your common one will have like usually a C involved, like the integration constant. When you integrate, you get a C left over. And then your particular, like if y equals 5 as a solution, then that's a particular solution, okay? And so where, okay, YC is a solution of, and then it's going to be like the same thing, but we're going to equal 0 here. So the common solution is the homogeneous solution, okay, and that would be something where the system is not being interacted upon by an outside force. And then Y particular is a solution of the one where it equals f of x, okay? So it's our, I call it a force solution. It's the forcing term on it. So, if you imagine like a bucket of oil floating in water, there's the internal motion of the bucket of oil just kind of naturally, and then there's the force of the water, right? And so we can talk about the motion of the oil inside of the bucket. And so there's both the homogeneous, the original bucket, as well as the force solution, which is the wave pushing on it, right? We can verify this if we wanted. Let's go ahead and verify this just to say we did it. So, to verify, okay, let's go plug it in, right? So what we're going to do is we're going to take the derivative with respect to x of our solutions, right, which we claim is this, okay, plus, and then p of x, right, times y, and we're saying y is this thing added together, right? So these two added together are going to be y, okay, and does it equal f of x, right? So can we put a little question mark above it? Does this equal f of x itself? And we can go check, right? So look, we have all of this. We're claiming that YC is the solution of this one, right? So then when we distribute all this, we would get the derivative of YC. So we would get d YC dx and then plus, and then we'll have the same thing but with a particular solution, right? You would distribute this derivative, And so this would then be a P for my particular solution. And then plus, and then we're going to have this P of X times YC. And then plus, and then we'll have our P of X times YP. And that would equal f of x. And I'm going to say f of x plus 0. You'll see why in a second. And so now I'm going to group these terms. I'm going to have the derivative common plus the p of x common. And then plus, very similar, we're going to have the particular plus this particular, right? So I'm just regrouping them. And that's going to equal this. And by definition, right, the see, if you come up here, this is this solution, right? And then this one's this solution. So that means y common, when you plug it in, it would equal 0. So this whole thing is 0. And then likewise, this whole thing is a solution of this, right? So if you plug this in, you would then just get the f of x and that indeed equals f of x plus 0, right? And so this works, and it is a valid solution. Okay, now that we're convinced that we have a valid solution, let's go ahead and see if we can derive what we would do with this. So what we're going to do is we're going to start, so to derive the solution, okay, and we're going to make us a formula that we can use, and it's not going to be as bad as it looks, but just follow me here. So step 1, what we're going to do is we're going to go ahead and set up our common solution equal to 0. We're going to set up this, right? So we're going to start with the common solution. So step 1, start with common solution, and we have that. Okay, so now we're able to actually rewrite this. I'm going to rewrite this as dy dx, and we just did that other section, right? So this shouldn't be too bad, equals negative of the p of x times y. Okay, and now off of that, so what I did was I moved this over, right? I rewrote that. So now I should be able to divide this y over and move the dx over. So let's try this. So this is going to be dy. I'm going to divide the y. So this, I'm going to move the dx over here. And you see what I have. So now I can integrate it, right? So I'm going to get the natural log of y, of the absolute value of y technically, is going to equal, and I have no idea what this is, right? But whatever it is, it's that integral. It depends what the function is. Okay, now that we have that, we can go ahead and e to that thing. So then we're going to get y equals e to the power of this. Okay? Absolutely amazing. So what we're going to do here is we're going to let, and then we're going to let y1 equal this. Okay, because that's the solution to the homogeneous equation that explains the internal dynamics. So this is going to be y1, okay? And in fact, we could probably let this be y common here. Yeah, let's just let this be y common. Okay, now to find y2. So step 2. Let's find, and then y2. Okay, so what we're going to do is we're going to go try to plug this in. Let's go find y particular. Sorry, later in life here, I'm going to call them y1 and y2. Okay, so we're going to have kind of the same thing, right? We've kind of got this, but we're going to set it equal to f of x. In fact, let's go grab that version. So we want this, right? We want it where it's equal to f of x. So let's go ahead and put that in. Okay, and we're going to use something called variation of parameters. So let's find y particular by using variation of parameters. Okay, I'm going to use this trick a whole bunch. Okay, it's kind of a dirty trick. So and now the y particular that I didn't know, right? What we're going to do is we're going to let it, and let's make it a function of x, right? It's going to equal, and we're going to call it u of x times, and then y common, which also happens to be a function of x. Yes, we should write that there. Okay, and so now that we have that, we're in pretty good shape here. We're going to use this variation of parameters, so I can make a y value from multiplying by a new function. We don't know what u of x is yet, but we know what y common is. Okay, so what we can do now is go ahead and take a derivative of this so we can plug it in. So I'm going to get the derivative of, and now I'm going to just name this uy. Okay, so y common, okay, over dx plus, and then p of x, right, times y, which is now uyc. You see what I'm doing? I'm going to plug this in for the y's, equals, and then f of x here. Okay, chain rule. So I'm going to get the derivative of like one of them, and then I'm going to hold the other one constant, right? So I'm going to get like u times, and then it'll be, so d y common, oh come on, dy common dx, right? And then plus, and then we're going to have this one here. So I'm going to have this p of x here. Okay, and, oh wait, no, wait, I didn't do it right. Chain rule, dude. So u this, and then I need the derivative of this times y common. So then I'll have du dx, and then y common, right? Oh, darn. Ugh. Y common. Okay, now plus this p of x uy. I can't really do much with these things, right? So they're kind of the way they are. And now, okay, it's all about grouping again, right? So, okay, this one has a u, this one has a u. Let's go factor out a u. And what I'm going to have left, I'm going to have this thing. Okay. I've got this thing without the u, so I'm going to delete the u. Okay. So when I multiply that back in, I'll get back my u. And then I have this other term. I couldn't factor anything out of it, right? And that'll equal my f of x. Okay. So, remember what we said, what this was, right? If you come up here, remember, this equals 0 because it was a common solution, right? So this equals 0, which just is going to leave me with this. I hope that makes sense because we defined it to be 0. So this whole thing right now is 0 by definition because it was the common solution, right? So now we're down to something that looks more like what we can handle, right? So now we've got this thing is true. The rest of that's 0, okay? So if we go down to our next line, we're going to look at that, and we should be able to solve that, right? So remember that y common is this, okay? So then that means that all we got to do is be able to integrate this, and I can get u. So then here's what we're going to get here, okay? Because you would plug this in for right here, right? So the derivative of this, so you're going to need to move it over. Here, I'm going to type that out. So we're going to have this, okay? Here, my next implies is going to be this, but instead of y common is this, right? So I have that here, okay? Now, I'm going to go ahead and divide it over, okay? So I'm going to take out that negative here, and so I'm going to end up with a positive on that side. So I'm going to have this thing here, okay, equal to f of x, right? But now times this thing, but I'm going to have a positive because like 1 over e to the negative x is just e to the positive x, right? So we have that. Okay? So now we can go, I'm going to need that. We can go solve for u. U is just the integral of this, right? So u of x that we were after for my variation of parameters equals the integral of this mess dx, okay? And remember what y2 was, or y particular. Y particular equals this u of x times my common solution. So y particular equals this, which happens to equal the common solution, which I already knew, and then this integral. Okay, I realize this looks awful, but you got to admit, I went and I found me a solution, right? So my general solution here, which equals my common plus my particular, so y common plus y particular is equal to, okay, my common solution is going to be a c, and then this thing, right? That's my common solution. And notice how I put my constant of integration with my common solution. plus, and now my particular, which happens to be this. And we're good? That is my solution. Okay, so we've now derived this from here, we should be able to go through this in a decent way that's not that bad, okay? So, method of handling. Okay, so one, you start off with this whatever form they gave you, right? We start off here. Okay? So we started there, didn't we? And then from there, you, let's tell us what we did. You're going to divide. Let's go get us a divided by symbol. Divide by A1, right? And that gets me this other form, okay? So whatever was there, now I divided by it and I got to here, okay? And then we got that, okay? So 2. From step 1, right above, okay? Identify this P of X, right? What is that? And what are you going to do with it, okay? And find the integrating factor. And we're going to name this thing right now so I don't have to keep doing this. And I'm going to keep this name. I'm going to name it mu, okay? And mu equals e to the integral of p of x dx, right? And that comes from this right here. That's our integrating factor, right? And now we're going to multiply it against f of x, and we're going to integrate that. So then from here, we're going to set it up as basically a backward product rule, okay? So this is going to be d dx of, okay, and it's going to be this integrating factor times y, and that's going to equal f of x times the integrating factor. Okay? From there, integrate both sides. Okay. I'm going to make another video with examples, okay? I'm going to pick ones out of your homework. I hope this made sense.